Good evening, everybody. Nice to see you. I'm Charlie Junkerman, the Dean of Continuing Studies, and it's my pleasure to just say a few words of welcome and then turn the podium over to Pam Matson, the Dean of the school. We just got email from a number of sources that there's been a car accident at the corner of Serra and El Camino, so people are drifting in late. I'm glad you're all here safe, and I'm sure you are too, and let's hope nobody's been hurt. Sorry? You can't hear me. You can't hear me? Wow, I'm sorry. What should I do? Now can you hear me? I thought I had a strong voice. Oh, that's better, isn't it? Is that better? All right, well keep, you still can't hear me? The tech guys maybe need to do some volume adjustment because, all right, is that better? That's probably better. Okay, shall I start again? Welcome, everybody. Nice to see you all here. I have just a few words of that to offer you. Welcome, and then we'll start in on our program for tonight. Tonight is the second in our quarterly series entitled Earth Matters, which is a collaboration between Stanford Continuing Studies and, we used to say, the School of Earth Sciences. Tonight's the first time that we, Continuing Studies, collaborate with the School of Earth. I thought I had it right. I will. Earth, Energy, and Environmental Sciences. Earth, Energy, and Environmental Sciences. Abbreviated, I'm told, to Stanford Earth, and also, rumor has it, sometimes abbreviated to SE3. Probably, if not yet, soon. So the School of Energy, Earth, Energy, and Environmental Sciences. And Pam Matson, the Dean, is going to give you a little explanation of why that name change seemed appropriate as soon as I finish. This series, Earth Matters, addresses a broad range of timely topics that are being studied by the faculty and students at Stanford Earth. They range from how our planet works or doesn't work, to the challenges, the resource challenges, the environmental challenges, the energy challenges that we're facing now and will face in the future. In the Earth Matters talks, faculty from the school, and tonight, for the first time, but not the last, joined by their graduate students, will talk about their current research, how they're addressing these challenges and problems, and bring you really some of the groundbreaking, pace-setting research that's being done at the school here at Stanford. I want to extend a special welcome to Pam Matson, the Dean of the school. Pam helped us put together this series, and in fact, she'll be the speaker along with faculty and student colleagues in the next Earth Matters program, which is on April 8th. It's on the back of your program, so please make a note of it, and when you get home tonight, put it on your kitchen calendar so you're sure to be here for what promises to be a thought-provoking and really enjoyable, informative evening. Before I turn the microphone over to Pam, I want to thank Rebecca Siegel, our public program manager, and Nancy Peterson, the director of communication for Stanford Earth. And both of them were instrumental in making tonight's program possible. We wouldn't be here without them. One other just quick reminder, you may notice that tonight's program is being videotaped. So when we get to the Q&A discussion time, please use the microphones in the aisle so that your question will also be recorded, as well as the answer that's offered by Noah Diffenbaugh and his panelists. So I gave it away. Noah Diffenbaugh is the faculty leader of tonight's panel, and he's joined by 3 of his chosen graduate students. But before they take the stage, please welcome Pam Matson, who is the Chester Narramore Dean of the School, and I've got it now, of Earth, Energy, and Environmental Sciences. Pam Matson.
Thank you. I don't want Charlie to leave yet because I know that it's hard to remember this name.
Oh good.
So we're giving him one of the first T-shirts of Stanford Earth with the new name, Earth, Energy, and Environmental Sciences. Thank you so much.
Thank you very much. Love it. Thank you.
But really, Charlie, thank you so much for all you do for Stanford and for education, and thank you so much for giving us this great opportunity. As Charlie said, we have a new name. We used to be the School of Earth Sciences, recently added Energy and Environment to that name, and we did that for a very specific reason. It better reflects the range of work that our faculty and our students engage in. For decades, for 50, maybe close to 100 years, the School of Earth Sciences has been at Stanford and has been very strong in understanding the subsurface of our planet, what people call earth sciences. And this is incredibly important work. Our faculty still are great in these areas, and we use that knowledge about the subsurface of the planet, the solid earth, to understand about earthquakes and volcanoes and tsunamis, to find resources, energy, mineral resources, water resources, and to simply understand things like the evolution of life on the planet. So, incredibly important area of science. But a few decades ago, the school decided to expand its reach into what scientists call the fluid envelopes of the planet, this narrow little envelope in which we live. The land systems, oceans, fresh water, atmosphere, and climate systems that are, in fact, our life support systems. And today we have a tremendously strong faculty in those areas as well. And we work on understanding how Earth works. We work on resources, including energy resources, and we work on environmental change in these systems, thus the new name. We continue to change. We have changed over time. We'll continue to do so as the challenges related to our planet change. Well, tonight's speakers are a perfect example of this new attention to the fluid envelopes of the planet and environmental change in them. Noah Diffenbaugh is a climate scientist, world-renowned. He's been a major player in the Intergovernmental Panel on Climate Change, the IPCC, a lead author in that. He is an editor of major journals in this area and an advisor to governments on these issues. He represents a range of knowledge that we are so lucky to have at Stanford. His own particular interests focus on this intersection between climate change impacts and our own vulnerability to climate systems changes. So he's going to talk a little bit about their work tonight in those areas. And as Charlie said, we're incredibly lucky that he decided to put together a panel of great students from our Department of Earth System Science. By the way, I should have mentioned, Noah is a professor in Earth System Science, a department in our school, and a senior fellow at the Woods Institute for the Environment. So we're very lucky to have him here tonight. I'm looking forward to learning from this conversation. And Noah, I will let you introduce your panelists, but please all come up. Thank you.
All right, it's a real pleasure to be here. I want to thank you all for coming out tonight and braving the flood in Coverly Auditorium, which happened a couple weeks ago, but that's how we got here. So an extreme climate event. Yeah, so I'm really excited about tonight. I think one of the things about being in a university and being a faculty member in a university that is really a special experience is getting to interact with graduate students. And I'm not aware of too many parts of the American industry where this kind of opportunity really exists. I think it's one of the unique opportunities that we have at universities, and certainly that graduate students have. It's an experience you can't really get anywhere else other than at a university. And I feel very lucky for a lot of reasons to get to be at a great university like Stanford. But consistently when I'm asked by my colleagues elsewhere, well, what's Stanford like? The first thing that comes to my mind is the tremendous quality of the graduate students that we have here at Stanford and the tremendous support that we have for for graduate students for training and interacting with graduate students, particularly the support like we get from the school, where graduate students really can have the opportunity to really focus on the research of their choice and not be bound by particular funding constraints from particular projects or things like that. So I think we're really lucky here at Stanford. So thank you, Pam, for all of the support that you give to all of us in the school. And thank you to Daniel, Deepti, and Justin for the fantastic opportunity to work with you all. I will say, I'm going to give a brief introduction to each of Daniel, Deepti, and Justin, but I do want to say there are three of a number of students working in my research group, and I think, as Pam said, they're representative of the high quality across the school and across the university. All right, so the plan is I'm going to say a few words kind of to introduce what goes on in our research group, specifically around the questions like Pam posed about climate and climate change and our risks and vulnerability and resilience in the face of climate change. And then I have some questions that I'm going to pose to the three students, and they're questions I've really been wanting to know their answers to for a while. So I'm excited that I'm going to get to find out what the answers are, and you will too. And then after that, we'll have quite a bit of time for questions and discussions from the audience. So that's the plan. To start out, I'm going to show a result from each of their work, but I want to introduce first Daniel Swain. Daniel is in his 4th year in the PhD program in the Department of Earth System Science, and Dan has been studying a variety of aspects of California climate in his dissertation work. He's equally famous for his California weather blog, perhaps more famous for his California weather blog, and which is very, very widely read, not only by the public, but also by real-world decision makers that are having to make decisions that depend on his climate blog in some cases. And Dan was recently named one of the top 10 young leaders shaping the West by Outside High Country News. Thank you. Deepti is in the middle, and Deepti is a 5th-year PhD student, and she is an expert in studying the statistics of climate phenomena and how particularly extreme events, and has published a number of already very influential papers on extreme events, including in the Indian monsoon, which is a really critical climate system globally. And Deepti is a Lieberman Fellow, which is one of the highest honors that Stanford bestows on graduate students. There's a handful of graduate students from across the campus that are named Lieberman Fellows each year, and so Deepti is one of the Lieberman Fellows this year. And Justin is a 5th-year student in the Emmett Interdisciplinary Program on Environment and Resources. EIPER, as it's usually known, and EIPER is literally, unique is a really overused word, and it's not used very precisely, but I will say that EIPER is a literally unique program. It's a one-of-a-kind program that we have here at Stanford in the school that brings together faculty and students from across the campus to work on interdisciplinary problems that can't be solved in any one domain in isolation. And Justin is a student in that program and also is a predoctoral fellow in the Center for International Security and Cooperation, or CSAC, in the Freeman Spogli Institute. Justin's work is focused on uncertainty and the variability in the climate system and how different human systems can integrate that uncertainty into robust decision-making about climate. All right, so those are what I know about the 3 students. I'm sure there's more that we'll learn. Okay, so I want to give a few remarks to frame our discussion. And we study climate. We study the current climate. We study the past climate, and we try to understand how climate might change in the future, and particularly when we get to Justin's work, how climate might evolve in the future and what the uncertainties are. And this is the record of global temperature. So this is from instruments around the world and thermometers, and also more recently satellite measurements. This is probably not actually a pointer. Okay, so what you'll see from the left to the right over the last 150 years or so is a clear warming trend. Right? So the global mean temperature has been increasing, and that is why we call it global warming. So I'm perfectly happy calling it global warming because the globe has gotten warmer. So as I say in my Earth Systems 10 lecture every fall quarter, global warming is an observation. It's not a matter of politics. It's not a matter of dogma. It's not a matter of belief. If you believe in thermometers, then you have no choice but to believe in global warming. It's simply something that's happened, and we've observed it. There's a lot of variability. There's a lot of noise. It's a chaotic system. But clearly, global warming is real, and it's statistically very significant. And we know with very high levels of scientific confidence that this global warming has been caused primarily by human activities, and of those primarily the emission of greenhouse gases, some from land clearing, but mostly from combustion of fossil fuels. And if we look back over the industrial age, we see that the United States has been responsible for about a quarter of the total emissions, the fossil fuel CO2 emissions, about a quarter of the total emissions over the course of the industrial era. And Europe has also been responsible for about a quarter. So about half of the burden of the global warming that is already in the system, what we've already seen expressed in the temperature record that I just showed you, and what's committed from the heat that's already accumulated in the ocean and the carbon dioxide that's still in the atmosphere, about half of that is from emissions from the US and Europe. The dots show observations of the last quarter century or so. So these are all real data up until 2013 in this case. And what you see is actually the global emissions, so year by year, the global annual emissions have doubled over the last quarter century, from about 5 billion tons of carbon to about 10 billion tons of carbon. So we're on a trajectory that is towards increasing emissions year after year, unless there's a financial crisis, which you can see right here. But we bounced back. We're back on trend. If we look forward, if we continue along this pathway that we're on now, we can expect about 4 degrees, give or take some uncertainty, but about 4 degrees of global warming above the pre-industrial level. We're already around 1 degree Celsius, so we're working our way there. But there's a lot more to come if we continue along this current trajectory. The UN has identified a 2-degree target as a goal. And so what you read about now in the newspaper, or maybe some of you might get your news on a screen now, I don't know, it's electronic or something like that, wherever you get your news. You'll hear about the UN negotiations, Paris, the COP negotiations that are heading towards Paris in December, and that what's being negotiated now it has a stated target of 2 degrees Celsius above the pre-industrial, so another degree beyond what we've already experienced. And as you can see from this blue curve, getting to 2 degrees requires a change in the trajectory. We are not on a 2-degree trajectory. And in fact, we've diverged from, we haven't exited to a 2 degrees trajectory. It'll really take turning the global ship around to get to 2 degrees, but it's possible. And that's one of the key points that I want to emphasize, is that the window is still open. It's still, the physics of the energy balance of the planet still make it possible that we can achieve that UN target. But it won't be achieved by continuing along the path that we're on, where the energy balance of the planet essentially guarantees that we'll blow right through that 2-degree target if we continue along the current trajectory. All right, so in our research group, we actually think a lot about what could happen to the climate system if the world continues along the business as usual. A lot of our work is focused on sort of understanding what the impacts might be from unconstrained climate change. But what I want to focus on today is the climate change that we can expect even if the world does achieve this 2-degree target. And one of the key points I want to make is that we have to adapt to climate change. Adaptation is not, well, I guess we don't have to. We could not. But there will be climate change to come. That's the point I want to make. Even if the international policy process is successful, that's targeting another degree of global warming beyond what we've already experienced. So there's no question that we're going to experience more climate change. And so a lot of the work that goes on in our research group now is trying to understand what are the probabilities of different kinds of climate outcomes, and what are the sensitivities of different natural and human systems to those kinds of outcomes. And that often ends up being about extreme events. And really, the way that we're thinking about this is very much in line with the current IPCC framing. So we heard from Pam about the Intergovernmental Panel on Climate Change. And we're lucky to have Chris Field, who's the co-chair of Working Group 2 here on campus on our faculty. And this is the framing from the current IPCC report, and very much is in line with my thinking and the work going on in the group. And that's a framing around risk. And as you can see in this petal diagram, the risk from climate, whether it's extreme climate events in the current climate or the risk of climate change, really results not only from the physical hazard, which is this petal, the darkest blue petal, but also the vulnerability of different natural and human systems and the exposure. So what are the assets? Not to be crude, but what are the assets that are exposed? That could be infrastructure, it could be people, it could be ecosystems, and how vulnerable are they? Right? So if a tree falls in the woods and no one is there to hear it, right? If a tornado happens on the northern Great Plains and there's nothing in its path, what's the risk? Right? So what gets hit and how vulnerable it is a big part of the risk profile. And most of what I'll talk about over the next few minutes is about understanding this hazard petal and understanding the probability of different kinds of outcomes. But then right at the end, when we leap off to the discussion, we'll touch on how this probability of hazards intersects with natural and human systems. So I said that we have some adapting to do no matter what, and I think we know this just from looking at the current climate. Right? So if we look at the U.S., if we look at the last decade or so, there have been more than 70 climate and weather disasters that each caused at least $1 billion in damage. Right, so that's on the order of 7 a year, where individually each of those is causing more than $1 billion in damage, and some of them are substantially more damaging than that. If we look at an event like Hurricane Katrina or Superstorm Sandy, It's looking like our current California drought predictions are that it's a $2 billion event, although those numbers are 6 months old now. We'll see where we end up. So a number of these events are more than, even more damaging. So the point is that just if we look at damage, never mind all the other stresses that people and ecosystems experience from the climate system around the world, if we just look at damage in the US, we know that we're not optimally adapted to the climate that we have right now. Right? We have win-wins where we can improve our relationship with the climate system, even without any further climate change. So it's often these kinds of events that we're focused on in the research group because humans are so, and ecosystems are so vulnerable to these kinds of events now. And for us, I think there are 3 key points if we're trying to understand the climate risks in the current climate and in this 2-degree window that the UN has targeted. One is that we have to understand the causes of particular events. So I'll mention the California drought in a minute. I'll mention extreme wet and dry periods in India. And these are instances where there can be very, very damaging events that are very complex and are very rare. And our approach is to first try to understand what the physical causes in the climate system are of those events. And then the second step is that we need to objectively evaluate if there have been changes in the probability of those conditions. And this can be hard because, as we'll see in a second, if we look at the California drought, for instance, it's an unprecedented event in terms of the precipitation, for example, the lack of precipitation, right? So we're often dealing with events where the event that's happening right now is the most extreme of any that we see in the observed record. And that becomes a difficult statistical problem to try to figure out the probabilities of events that fall outside of our historical experience. And I want to mention now that our research group's been collaborating with Professor Bala Rajaratnam, who's also in the school, and the Department of Statistics, and that's been a very fruitful collaboration across the school to understand these rare events. And then the last thing that the last step is to figure out how we can objectively test whether global warming has played a role in those conditions, and particularly the probability of those conditions, whether it's drought in California or flooding in India or any number of other high-impact events. And you'll read different things in the media from different people. And my view is that there's no reason that every event has to be caused by global warming. There's not some law of the universe that says that if it's extreme and it had an impact that global warming is the culprit. And we're really working hard to try to be really objective and really disciplined and really, from a scientific perspective, conservative, and only make a claim that we've found an imprint of global warming when we're very, very confident that that's the case. So we can talk about that perspective as well. All right, so now the home stretch. To introduce the students a little bit. So Daniel Swain, I mentioned Daniel Swain has been working on the California drought, the ongoing California drought. We used to say the 2013 California drought, and then we said the 2014 California drought. Now we're just calling it the ongoing California drought. It's timeless. So this is a plot in the upper left from Daniel's paper that came out in September. And what you're seeing along the bottom here, the horizontal, the letters are just the first letter of the month, right? So you're seeing January, February, March, April, May. So just the calendar. And each of these gray lines is a year of real precipitation observations from California. No climate models, just the rain gauge data from across California. And each one of these gray lines is a year. We have about 120 years of historical record from California. And the dashed line is the mean of all those years. And the red line is the calendar year 2013. So this paper came out in 2014, so we were working with 2013 data. And what you see is that by the total, this is cumulative, so it's you look in December and you see the total precipitation that fell in each of those calendar years. And you can see that 2013 not only was the lowest total calendar year precipitation on record, but was also about a third of the mean, the long-term mean, and just a bit more than half of the second lowest year in the record. Right? So this is an extreme, extreme event, much more extreme than the second most extreme event in the record. And I mentioned the $2 billion figure. So this is a table from the report from UC Davis that came out this summer on impacts of the drought. So just to give you a sense, their calculations are about $1.5 billion in 1.5 billion. Sorry, not 1 billion and 50 cents, but $1.5 billion in direct losses from the drought. About a little over $2 billion for the total economic cost, and that includes the loss of about 17,000 jobs, and some of them seasonal, but an employment impact of about 17,000 jobs. It'll be interesting to see when these numbers get updated, but there's no doubt that this is a natural disaster. This is an ongoing, very high impact event, and we're feeling it locally, and some people are feeling it even more acutely where they're not able to take showers, for instance, because the groundwater is the wells have gone dry. One quick note on the extremity of the event. Just this afternoon, Daniel sent me the latest snow measurements from Donner Summit. I believe this picture's from Tioga Pass, but from the snow measurements from Donner Summit that have just come out show that right now, for the year-to-date snow total, this is the lowest on record. So 2015, the other day of 2015, we're now at the lowest snow total for this time of year that on record. So we're still we're very likely to continue to be in a drought when this rainy season ends, and then we'll be back to the warm and dry. All right, so Daniel's, if any of you have heard this term or read this term, the ridiculously resilient ridge, Daniel coined that term, and I mentioned to Daniel the other day that I think that the proof that something you've coined has really made it is when it's in the New York Times and it's completely unattributed. They don't even bother to say where the term came from, and so Daniel has reached that point of anonymity where he's had so much impact that nobody bothers to credit him for it anymore. So this ridiculously resilient ridge is this feature in the atmosphere that has been coming and going during the drought, but was extremely persistent. One might call it ridiculously resilient even during calendar year 2013. And essentially, if living here in the Bay Area, I'm sure you're familiar. We get our storms kind of carried along these storm tracks across the Pacific, and the ridge in the atmosphere, it's an area of high pressure, and it's essentially like if you threw a boulder into a stream, right? The water's going to go around the boulder, and what this ridge has done when it's been present is it's steered storms away from California. It's blocked storms from reaching California. I think we're seeing some interesting things with snow now, where it's been so warm. As Daniel's pointed out on his blog, with this last storm, that even when there's been precipitation, high elevation, it's been so warm that it's been tough to get snow. So I think we're seeing a lot of new things in this drought, but certainly the main contributor has been that we just haven't been getting the precipitation arriving. And so Daniel's been the person in the country that's been identifying this, and his paper that came out in September was focused on the probability of these extremely high and persistent pressures over the Northeast Pacific, and what we found in that paper was that at the 95% likelihood, as again I say we're conservative in our statements, so we're very, very likely that global warming has at least tripled the probability of these conditions in the atmosphere occurring. They're still rare, but less rare than if there hadn't been any global warming. So Daniel's going to tell us more about that. So next up, a figure from Deepti's paper that came out earlier in, I guess a little less than a year ago. And what Deepti attacked was this really difficult problem of extremely wet and dry periods that happen during the monsoon season. And the monsoon in India, Deepti, correct me if I'm wrong, but something like 40% of the population sort of lives within the drainage basin underneath the monsoon. So it's a big, billions of people depending on the monsoon, and it has a very clear seasonality, and there's a tendency to think of it as either on or off. The monsoon hasn't started, then the monsoon starts, and it's the monsoon season, and then the monsoon ends. But the reality is that there are these oscillations that happen during the monsoon season, and they can have really extreme impacts, both if there are very wet, short periods within the monsoon season, or if there are very dry, protracted periods within the monsoon season. Because most of the agriculture is rain-fed. There's not a lot of infrastructure or other capital for resisting flood events. And so it's really often these extreme wet and dry periods during the monsoon season that can have very big humanitarian impacts. And it's a very difficult statistical problem because we have relatively short record from India, about 50 years of daily scale observations for the countrywide network. The oscillations make it that there can be very few of these events in any given year. So it's a difficult statistical problem. And what Deepti did was she constructed some sophisticated statistical tools for testing hypotheses about different characteristics of these extreme wet and dry periods that happen during the monsoon season. And she found, for the first time, that there's been a statistically significant trend towards increasing intensity of wet spells. So when these short wet periods during the monsoon season have happened, they've been getting more and more intense over the years. And also at the same time, the dry spells have become more frequent. So both more intense wet periods and more frequent dry periods. And what Deepti's working on now, we were looking at results today using climate models to try to understand whether or not global warming has played a role in these trends. We're agnostic. Our null hypothesis is that it's all noise, it's all random chance, but we're framing hypotheses and trying to test them. All right, so third, last but not least, some of Justin's recent work, and I'll let Justin explain more of this, explain this in more detail. But up in the upper left, you see a schematic of the importance of understanding the range of possible climate outcomes if humans are going to make decisions that are robust to the uncertainty in those outcomes. So if we imagine that this dashed line is the present climate, some distribution of some climate variable, say it's spring snowpack in the Sierras, there's some distribution across the years. And if all we care about is the mean, then we might say, well, the mean snowpack is likely to decrease, and we know that actually with high confidence that that across the northern hemisphere, this spring snowpack is, for most areas of the northern hemisphere, with the exception of Northeast Asia, that the spring snowpack is very likely to decrease. If all we know about is the mean, then we might just conclude that we don't actually have to make any real change in our system, that the mean decrease won't be sufficient to really push us in any kind of stressful zone. But if we look at the variability that goes with those changes in the mean, and particularly the uncertainty in exactly which pathway the climate system will take, then we might get very different outcomes that are consistent with the same mean change. And that's what these blue and red lines represent. And it's important to know if the range of outcomes is in the red, in which case the possibilities range from no change in our water management system to maybe bringing on some new storage that can handle dry years, store some more water in the wet season to handle dry years. On the other hand, the blue PDF implies a much bigger range of possibilities that might require coming up with alternative supplies that come outside the range, changes that come outside the range of just bringing on new storage. And so this is a schematic, but Justin has been testing this in some more practical settings, such as the uncertainty in snow accumulation and melt in the northern hemisphere. And so I'll let Justin say more about that in a minute. So that's the overview, and I want to thank you for your patience in listening. What I want to do now is just, I said I had some questions I've really been interested in asking the students. So I'm going to do it now, and we'll listen and hear what they have to say, and then we'll open up the floor for questions from the audience. So the first question, Daniel, which I'm sure I'm not the only one wondering, what is going on with the drought? What's causing this drought that we're experiencing in California?
All right. Well, as you so succinctly alluded to in the introduction, droughts are typically associated with a lack of rain. When you think of drought, you think of dry conditions. And those of you, well, if you've lived in California long enough, you probably realize that we have sort of a unique situation here in terms of climate, in that we have a really distinct rainy season that happens to occur during the winter. And our rainy season is usually characterized by periodic storminess. We get rain on and off throughout the winter. It doesn't rain every day, but it does rain on a fairly regular basis. Well, at least it used to. And some of these storms are big, some of them are not so big, some of them are really big, and if you've lived here long enough, you remember some of these really big years in California where you just have these unending sequences of really heavy rainfall events that cause flooding and mudslides and problems. And those really wet years are sometimes punctuated by drier years, and usually the difference between a really wet year and a really dry year is the occurrence of fewer storms versus more storms. And what we've been seeing over the past few years, again, as you mentioned earlier, is that most of these storms that would normally be making it to California during the wet season in the winter have instead been deflected to the north of California, into Alaska, and to British Columbia. And so while those places have been extraordinarily extraordinarily wet, we've been sort of extraordinarily dry on the southern end, and the proximal cause of this shift in the storm track is the ridiculously resilient ridge, this persistent region of atmospheric high pressure over the northeastern Pacific Ocean that just keeps pushing storms to the north. And that region of high pressure has, again, as you mentioned, come and gone over the past few years, and it is something that does occur periodically in this part of the world. But what's really remarkable about the last couple of years and this whole drought sequence in general is that this ridge keeps coming back. It keeps deflecting the storms away from California, and it is indeed has indeed made a reappearance over the past couple of months in California.
So, Deepti, what Dan just described sounds complex and rare, and we've seen the statistics that it's really outside of normal. So how do we go about figuring out if this is just the black swan sort of event, or not, and if the probabilities have changed, if these kinds of conditions have become more or less frequent in the more recent period? How do we go about trying to answer that question?
So we do have only one observation of the Earth system. We only have, for most events like these, we have about 60 to 70 years of record. And so since we only have observed the world with climate change, we use climate models, which are physical models of the Earth system. They use mathematical equations, physical equations, to describe fluid motion and other processes that govern the climate on Earth. And we can essentially run these models under different climates. So we can run it with the anthropogenic forcings, which are like greenhouse gases and aerosols, and try to understand how each of these forcings or these factors that influence the climate have affected the probability of an event like this. So we can say, well, how often would an event like this have occurred if we didn't experience the anthropogenic greenhouse gases that we currently have in the atmosphere? Or we could ask the question, well, given that this event occurs, how intense is it, and why is that intensity affected by the presence of greenhouse gases? And so we can quantify the risk of such an event, the risk of occurrence, as well as the intensity of such events using climate models.
So everybody knows that climate models are wrong, even those of us who spend all of our time with them. So Justin, how do we, given that these are rare events and that we're relying on short observational records and we're relying on, we only have this one realization of the climate system, and so we need to use these mathematical models to get more information about how the climate system works. What's a decision maker to do, and how do we, as scientists, what can we provide that's both credible but also actionable, and that incorporates all the range of uncertainty in a way that a decision maker can make a decision?
That's a really hard question to answer. I think an alternative way of thinking about it is climate science presently positioned to inform the adaptations that are going to be necessary as the effects of global warming manifest over the coming decades? And I think the answer to that is yes. I think there is a tremendous amount of information that can be provided to decision makers, and one of the ways of thinking about that is to not assume that uncertainty about what's going to happen in the future is something that actually hamstrings effective decision making. In fact, it's the alternative. We make decisions under uncertainty all the time, and so there are plenty of decision science tool sets that can deal with different ranges of uncertainty. And one of the things that we've been able to do in the last few years in climate science is because of efficiency increases in computational resources, we're actually in a position to simulate, using some of the Earth system models that Deepti was talking about, simulate the projections of climate many, many times, which gives us a better estimate of uncertainty in what's going to happen. So from a decision standpoint, an adaptation decision maker wants to make what are called robust adaptations. And that figure that Noah had showed earlier, which had the probability distributions of snow, a robust adaptation decision is one that's beneficial under the broadest range of potential outcomes. So in fact, understanding the full range of uncertainty actually enables rather than disables decision making. And because of computational efficiency increases in running our simulations of climate, because that is the only tool set we have, we're actually able to characterize that probability distribution much better than we have previously, which is of huge advantage to decision making over the near term.
Excellent. Now I know the answers. All right, so we can keep talking because we have lots to talk about. But I'm interested at this juncture if there are questions from the audience, and if so, as was mentioned earlier, we are being videoed. So if you can come to the microphone so that gets captured, that would be most helpful. All Oh, we've got one.
I'm Bruce Daniels, and my interest is in hydroclimatology research. And probably as you all know, the climate models do a good job of forecasting temperature. There's some spread among the 40 models that the IPC looked at for temperature, but for precipitation, they do a lousy job. In fact, it's very difficult across the surface of the globe to find places where there's a substantial number of models that even agree on the sign. And so if you don't really know whether it's going to get wetter or drier, whether to plant cactus or put it in a rice paddy, statistically, how do you deal with those so you can get sensible, adaptations that you can believe in?
Well, I'm interested to hear the others' comments, but I do want to clarify one point about the IPCC projections in the model agreement, because this is something that I've spent quite a bit of time on over the last couple of years, and it's amazing to think how many hours and days and weeks and months have been spent on deciding which part of a map should get a black dot and which part should get a black X. And if you look at those IPCC maps, we spent a lot of time trying to figure out how to communicate that uncertainty that you're talking about. And I think one of the big steps forward that we've made in this current assessment is distinguishing between where the models actually disagree on the sign and where the models actually agree that there's not likely to be a statistically significant change in the precipitation, or the temperature for that matter, but it's somewhat irrelevant for temperature because of because it's significant pretty much everywhere. But for precipitation, actually most of those places that in the fourth assessment were perceived as having model disagreement about the sign, most of those places at the annual scale for precipitation actually have very broad agreement across the climate models of a lack of statistically significant change in the annual scale precipitation. And now that doesn't mean that there isn't a likelihood of other kinds of changes, particularly extreme wet events. Actually, if you look at the map of that metric, actually there's very broad agreement across the climate models that the wettest events of the year are likely to become more frequent and more wet. And also that the frequency of dry days also is likely to increase, and that also has broad agreement across the models. Are there other thoughts on that? I know, Justin, you've been dealing with precipitation uncertainty quite a bit.
I think one of the things that has come out of some of the work that I've been doing, which uses a single climate model. So let's pretend we know with perfect certainty the model that's the right model to be using. So we can say that any kind of uncertainty from the model being incorrect is 0. And let's also pretend that we know the greenhouse gas trajectory we're going to be on going out into the future. So the ambiguity about people's greenhouse gas emissions over the coming century, that uncertainty is 0. So those are two major sources of uncertainty in our projections of climate change. So the only uncertainty that's left based on how climate scientists typically partition uncertainty is what's called internal climate variability. And these are the variations in climate that happen in absence of any forcing. They just the oscillations that occur from year to year. And when you simulate with a single model in a single forcing pathway many, many times, what you actually find is that internal variability, which is just the year-to-year variations, can actually stack up on each other and create persistent trends that can, as we know, enhance things like global warming. It can diminish the effects of global warming. And in fact, it can reverse our expected trends in global warming. So a place that we expect to get wetter could, in effect, get drier just from this what's called irreducible uncertainty. And what that tells us is that a kind of a subtle interpretation of that is that to the extent that we believe these models are capturing the Earth system processes we care about, that there is a level of uncertainty beyond which we cannot reduce our projections of climate change. And that uncertainty is of sufficient magnitude to reverse the trends in hydroclimate. So it can make a place wetter, or it can make a place drier with the same forcing. And I think that's a really important thing, because that tells us that some of what we've been attributing, some of the uncertainty we've been attributing to differences among the models is actually incorrectly classified. It's actually uncertainty from internal variability. And that's a really important point from a decision standpoint, because it says that that this is irreducible uncertainty in the climate system and is not a function of an immature science or not being effectively positioned to inform decision making, that this is just the uncertainty that is an innate characteristic of the climate system.
Thank you, Justin.
Sure.
Yes, sir. Oh, sorry, you were next.
Thank you. Following again along the lines of trying to deal with uncertainty, that's such a huge question for the public and for leaders to deal with and try to, when you're considering changing economies and turning a ship the size of civilization. I still have a very hard time gauging, in spite of these interesting answers, gauging the confidence in prediction. One thing that I'm not sure I understood from the discussion so far is the relationship between the observed variabilities, extreme events that you talked about and you've all talked about, and the models themselves. I mean, do the statistics of increasing extreme events on their own, standing on their own, can you make predictions based on those, or do you have to use climate models with all their limitations in the boundary conditions, inputs, and everything like that, which in fact, you made a comment which I didn't quite understand. You said, as we all know, climate models are wrong. Maybe you could.
Well, there's a truism that all models are wrong and some models are useful.
Okay.
So I was referring to that.
All right.
So I think we use climate models because we're very conservative, right? So if we can look at the trends in the observations, and if we just look at the trends, there's no question that the climate is changing. Not only that global warming is occurring, but that many kinds of extreme events are increasing. They're increasing in frequency. They're increasing in magnitude. If we rely only on observations, then I think we have no doubt that if we just project those trends on into the future, then we can expect greater stresses from the climate system. And so we use climate models because we're conservative. We don't want to simply attribute trends to humans because we see trends in observations. We want to understand what the causes of those trends are. Right? Because it is a noisy system, and it's possible that trends could occur by chance. So the reason we use models is we want to understand the physical processes. If we want to rely only on observations, then it's an open and shut case. There are a mountain of observations from all around the world. Not only that climate in the mean is changing, but that the extremes of climate are changing, and that those changes are having impacts on natural and human systems. Yes, sir.
The ridiculous ridge.
It's ridiculously resilient.
I just decided to shorten it.
Fair enough.
We heard that the ridiculously resilient ridge pushes the storms further north. They miss the Sierra, they miss us, they miss California. The next question that comes up is, what causes the ridge to move and be resilient? I've read a few places that that's because the Arctic is warming. I wonder if you'd pick up on that and respond to the question of why that ridge is moving, and and why is it so resilient?
Well, that's an excellent question, and sort of gets at the heart of what several of us are actually sort of thinking about right now. It's a lot easier to say that the proximal cause of the drought is this ridge, but then going back a step further and asking what the physical causes of this persistent ridge are. And the answer, you may not be surprised to hear, is that it's complicated. But there are some emerging hypotheses as to sort of what might be going on that would cause this really anomalous feature to persist, not only within seasons, but also between years. And again, that persistence aspect, that resilience really is the part of this phenomena that is so unusual. Because again, we tend to see these ridges periodically for short periods of time, almost every winter, but they typically don't last for months on end and then recur with that sort of tenacity over years. And typically when you see any sort of persistent atmospheric pattern, anything that lasts for an unusually long period of time, really anywhere on Earth, usually the root cause is somewhere in the oceans, and that's a very broad answer, but a lot of the time what's going on with the oceans, whether the oceans are particularly warm or particularly cold, or whether the spatial patterns of warm and cold in the oceans are unusual, typically the oceans are the sort of the memory, the stored information in the climate system, and so when you see these things recurring over and over again in the atmosphere, usually there's some kind of anomaly in the ocean that's driving that. And so in the case of this particular event in the northeastern Pacific, this persistent ridging event over the past couple of years leading to the drought, there's an emerging thought that there might actually be some unusual things happening in the tropical western Pacific Ocean, so unusually warm conditions very far away from where the ridge actually is. It's also true that the whole northeastern Pacific has also been really, really warm these past few years, and that may sort of be a reverse causality. The ridge is causing the warm water, and then the warm water sort of reinforces the ridge, and so that gets at another interesting point about the climate system, is that there are these self-reinforcing feedback loops that tend to develop when you have these sorts of persistent patterns, and again points at sort of the complexities of using climate models on a system that's so dynamically complex and where everything is sort of interconnected. But a really general answer is that at least part of the persistence of this ridge is probably due to these unusual ocean conditions, both the warm tropical West Pacific and then partly the feedbacks that are occurring in the North Pacific as well. You also brought up the Arctic. That's a current hypothesis out there regarding the sort of the persistence of weather patterns in general. There's some evidence for that. It's still sort of a young idea, and part of the problem, again, is sort of this observational uncertainty that we've been talking about. The changes we've been seeing in the Arctic, losing all of this Arctic sea ice volume, losing this high latitude snow cover, has happened so quickly over the past few decades that we still have a relatively short period of observations to see how that's affecting the climate system. And because the natural variability within the climate system is so large, it's taking a little while to be able to detect trends and what the influence of these high latitude changes elsewhere. But it's a mechanism that may be in play. I don't necessarily think we have enough evidence to say for sure yet.
Dean Matson.
Thank you all very much for this. This is great. I have a question about the increasing intensity of precipitation events. I think there are a lot of places around the world where the trend is that annual precipitation may not have changed, but that rain is falling in much more intense and fewer intense events. And of course, that has a lot of consequences for urban infrastructure and agriculture and everything else. And so I have two questions about that. One is, what do we think for California? Is there any information that would allow us to first ask if that's happened here and if we're projecting it to be an issue for us? And then I want to go to Deepti to talk about the monsoon systems and just what are the big consequences there, and is this something that's actually being paid attention to by decision makers in that region of the world?
Can we start with Deepti?
Okay, so for California, actually, some of the research that I've done is using high-resolution climate models, which basically simulate the entire continental U.S. at a 25-kilometer resolution. And that's a pretty high resolution compared to the global models that, that are part of the IPCC Intergovernmental Panel on Climate Change report. And from my own study, it looks like California is going to get consistently drier in all the seasons. And some of those changes which are outside the range of the present variability are likely to emerge within the next 20 to 30 years. And that is going to, the drought is going to intensify as you go out into the 21st century. And the global climate models actually, they are a little less certain about those changes. So I think Daniel can talk a little bit more about that. So for the monsoon, we've seen an increase in, not just in the monsoon season, but in other regions as well. We've seen an intensification of rainfall, which is it's like a first order effect to increase greenhouse gases and having a warmer atmosphere. The effect, so as Noah mentioned, we have a large percentage of the population in India still depends on rain-fed agriculture, and so they plan their planting based on when the monsoon onset is likely to occur, and they plan their field preparation and all their activities around that, and so either when the rain doesn't occur or when it's too intense, it affects their planting. It affects their depending on when these extreme events occur, it can affect the yield of these of their crops. So one of the regions that I visited last year had, I'd gone there in August, and the monsoon typically occurs from June through September, and even in mid-August, the monsoon onset had not occurred. And then while I was there, there was a brief rain spell, and everyone decided to plant their crops because that's the only opportunity that they have to plant their crops. And so then they did, and then again, the monsoon went into a dry spell, and they didn't have any rain. But even then, they still did have some yields, some crops growing. But then they were hit by a cyclone that occurred during the monsoon season, and that completely wiped out their crops. And there's nothing they can do if these events, if they've planted a crop and they have an extreme rainfall event, there's nothing they can do to rescue their crops if it occurs late in the season or during their planting season.
Yes, I think that's indicative of what we see in observations across much of the globe, of increasing intensity of rainfall events coupled with longer dry spells. And this is something that was predicted, I'm trying to think what the reference here for Trenberth's paper is, but I think 1999, Trenberth 1999, we can Google it and confirm. But so this is something that was predicted as Deepti says, is a first order effect, not only the increasing water vapor in the atmosphere that's from thermodynamic predictions that are century old, but the effect on the intensity of wet events followed by longer dry spells was laid out theoretically and then has been corroborated with observations from around the globe over the last decade and a half. So I think it's something that is a very clear, both a clear observation of changes in the climate system, but also something that has been formally and scientifically, objectively attributed to the human emission of greenhouse gases. Right. So these changes don't occur in absence of the atmospheric warming that has occurred over the same period. Yes, sir.
So my question really has to do with the intensity of climate change in general. That to put things in perspective, I don't remember that I've really ever heard anybody describe compared to the pre-industrial average mean for eras in the Earth's past, when it was considerably warmer and wetter or considerably colder. What was the difference between the mean temperature in those times compared to currently? So like when we are talking about, okay, so a 2% increase in average temperature currently, if that's the desired goal, how does that compare to these episodes in the past?
great question. Yeah, so Chris Field and I had a review that mentioned Chris earlier. So we had a review published in Science in 2013, and one of the parts of that review was we went back and asked this question from, neither of us is a geologist. We went back and just looked at what has been published in the literature across the last several decades, and we know from so geologists, including experts in our School of Earth, Energy, and Environmental Sciences, which I can now say very quickly, or SE3. People like Rob Dunbar and Paige Chamberlain and Kate Maher, right, they've developed geochemical techniques to look at soils or look at coral skeletons or look at the gas bubbles in ice cores, for example, and reconstruct what the temperature or, in some cases, precipitation or sea surface salinity or other environmental variables was at different times in the geologic past. So we know from that kind of geologic work that the last glacial maximum was about 5 degrees Celsius colder than the present. So that's 3 to 5 kilometer thick ice sheet over North America down to Kansas, basically. Right? I mean, that's a really different climate, and that's 5 degrees Celsius. And it was thousands of years to go at a global scale from 5 degrees cooler to the pre-industrial climate. If we look back, we have to go back further in time to find warm episodes. There's the Pliocene is one that some people look at about 3 million years ago. If we look back at where do we find the last time that that global greenhouse gas concentrations were 800 parts per million, 900 parts per million, 1,000 parts per million, where we're headed on that business as usual trajectory over the next, if that goes on for a century, we have to go back 20 million years, some reconstructions 50 million years to find a period like that. And one period that's been very heavily studied is the Eocene or the Paleocene-Eocene thermal maximum. And this was a period 55 million years ago when there was about 5 degrees of warming. So something like that business as usual trajectory that we're talking about. But the difference was that it happened in probably more than 10,000 years, at least more than 1,000 years, right? So at least an order of magnitude slower to get the same amount of warming that we're looking at over the next century. So that velocity that we're looking at for a global scale warming is at least 10 times faster if we just continue doing what we're doing than the last time we see anything like that in the geologic record. I will note that during that period, it was a very different climate. The Arctic was ice-free, at least in the summer. The temperatures of the Arctic Ocean were very similar to the temperatures of coastal Florida now. Unsurprisingly, given that piece of information, the flora and fauna of the Arctic were very similar to coastal Florida. There's very clear fossil evidence of alligators and palm trees living inside the Arctic Circle. The world didn't blow up, right? Life didn't end, but it was at least 10 times slower to get to that condition. The alligators had at least 10 times as long to get from Florida up to the Arctic Circle, and they made it. We're looking at that level of change, but at least 10 times faster. And that's a very good point. So there was the landscape was different than it is now. And yeah, it's a great point, is that we're, and actually a lot of these studies that have been done about velocity of climate change and how fast in the current climate different species, both plants and animals, can respond to different rates of change. One of the things that people consider is the fragmentation of the landscape. It's one thing to be able to disperse across an unfragmented landscape. It's quite another to have to disperse within the landscape that plants and animals encounter now. Yes, sir.
So how did 2014 compare to 2013 for the California drought? And also your reaction to the recent news that a leading climate change denier had been receiving a lot of funds from the oil and gas companies?
Daniel, I'm going to ask you to answer the first question.
All right. Well, as you mentioned, the drought continues. 2013 was the driest calendar year on record in California. 2014 was still another dry year, though not quite as dry as the driest year on record set the year before. Really what we have at this point is a sequence of three years that put together are the driest 3-year sequence in recorded history in California, which goes back around, well, over 100 years, in some places back over 150 years in California's record. 2013 and 2014 together were among the driest combination of 2 years in the full record. And what's happened over the past couple of years is that we've seen the drought started sort of very suddenly, where precipitation just sort of shut off in late 2012, continued all the way through 2013. We got a little bit towards the end of last winter. We got some rain and a little bit of mountain snow, although I do say a little bit relative to what we would normally see in the middle of our rainy season. The beginning of this winter, you may remember, it actually rained a lot in early December. In fact, I believe Stanford campus or the Palo Alto area actually saw one of its wettest 24-hour periods on record all of a sudden out of nowhere in early December. That's associated with one of these storms that we call atmospheric rivers, which bring these prodigious amounts of moisture up from the subtropics and can dump a lot of water on coastal California really quickly. And so if you look at the calendar year 2014, you capture the fact that we had a couple of really wet days in December. And as it turns out, those really wet days in Northern California are enough to make the year itself look like it wasn't all that dry, even though anybody on the ground would tell you that it was a very dry year, except for those 2 days when you didn't want to go outside without an umbrella. And interestingly, the very early part of the current calendar year, 2015, is sort of behaving similarly, where we had one of the driest, or one of the longest, if not the longest, midwinter dry spell on record in the Bay Area for the second half of December all the way through January, and then up right to the beginning of February, where we again saw another period of really intense precipitation, but very brief precipitation that again shut off completely after a couple of days. We're once again in a long dry spell. And so sort of what we're seeing, the beginning of the drought was extremely dry. There just wasn't really any precipitation anywhere in California. And that's sort of transitioned into a slightly different drought state where now we're getting these really intense, really warm, and that's another important point I think we'll talk about in a bit, these really intense, really warm, really brief downpours interspersed between record dry spells. And so when you look sometimes at certain calendar intervals, it doesn't look as dry, except when you look at what's going on in terms of the precipitation intensity and the dry spell intensity and the fact that we aren't getting really any snow in the mountains. All of that really continues to add up this year and in 2014.
So yeah, I think Daniel brought up temperature, and check back on Monday for the word on temperature in the California drought. I'm not joking. Monday's the day. We have a paper that's in press that'll be coming out on Monday, and it's embargoed. It's a big secret. If this wasn't being videoed, I'd tell you all about it. And if you didn't have Twitter, Twitter's the real thing that hurts the embargo.
But we can talk about an anecdote about this year.
Well, I want to answer the question about objectivity, and I think one of the real foundations of science and the scientific process is our peer review system, our system of scientific publishing that relies on peer review, relies on self accountability and declaration of conflict of interest. And Pam mentioned that I'm an editor of a journal. It's a society journal. I'm proud that it's published by a scientific society, and certainly we're very serious about making sure that the peer review process, the institution of the peer review process has integrity and is maintained. And so certainly my answer would be that in everything that we do in our research group, we work very hard to maintain that integrity and that transparency. Yes?
I'm aware that it is 10 months away before we will have the climate conference in Paris. Also that there are huge hopes for that conference to produce something that can actually change public policy throughout the globe. My question is, could you give us a sense at this point in time what your own expectations are for that meeting? And are you optimistic, pessimistic, or completely uncertain?
Well, so I'm only a citizen that reads the newspaper and listens to the internet, radio on the internet. So the people that I know that follow this and study this, they say that Copenhagen never had a chance. That for months in advance of Copenhagen, anyone who followed policy knew that, followed the international landscape, knew that Copenhagen never had a chance, and that Copenhagen never had a chance because there was basically no moral authority from the U.S. And so for me as a citizen, if you're asking me what are the odds of Paris relative to previously, I think that just as an observer, that the fact that the U.S. has now these basically bilateral agreements with China and India, that the three of the major emitters that didn't really self-bind with Kyoto ever, and that are perceived as being barriers to the international process. The fact that all three of those have basically committed to self-constraining within these bilateral sort of announcements, I would say that increases the odds of an agreement being tractable. I really don't know the ins and outs of what's going on, the nitty-gritty of it. But I am quite certain that those were big steps. So the EPA, the EPA regulations that are domestic for the U.S., the commitments, the joint commitments for the U.S. and China, the joint commitment for the U.S. and India, those are different than what we've had on the landscape previously. I think we have time for one more question, if anyone has one. Oh, there's a race. There's a race either for the door or the microphone. It's unclear which.
Try to be. My name is Barbara Graves. I'm an environmental activist, and I'd like to thank you for a presentation that I mostly understood. So thanks a lot. My question concerns not the crises themselves, which are big enough, but to me as an activist, what frames all of these crises is a crisis of communication. Let me give you just one example. With water resources, when we're trying to get decisions made about climate change, how to adapt to it, what we can do to help the dry climate in California, it comes down to, is the public willing to build stuff? Like the broadest adaptation is going to be for projects. Things like water recycling plants or, desalination plants, things like that. So what I see as an activist is an alignment of the right and the left against building stuff. So I've been working on the assumption, well, if only people had enough information, they would come to agreement. And I don't believe that anymore. I think, just information isn't enough. So I got really hopeful when you mentioned the interdisciplinary group here at Stanford and wondered if they're dealing in issues of how to communicate to the public when information has not been enough to spur the public to action.
Well, so literally the best person to answer that question is here. Dean Matson, who is the director of the Aldo Leopold program and many other efforts. So I think it would be wonderful if you would close us out with an answer to that question.
Okay, yes, the question is, is communication enough? And if the scientific community gets better at it, will it really make a difference? And I for a long, long time, as a leader of a leadership program for academic scientists who work on environmental issues, thought that we just needed to be better at this. We needed to be better communicators. And I think we've gotten to be a lot better communicators around the country and around the world. And I agree that it hasn't been enough. What we need is leadership. We need leadership in political organizations. We need state leadership and national leadership and international leadership at the political level. And so, I'm always very happy to be in California because at least I see us trying, having conversations, putting in effect bills like the recent one around water resources that sets us on a track. I think that interaction between the scientific community and policymakers and decision makers like everybody in this room is really an important part of that. But just saying scientists need to be better communicators is just not the answer for that. I don't know if that really addresses your question, but it's a good one, and we can pick this up after we close. I think it's probably time to say thank you to all of you for being here, and thank you most of all to this absolutely wonderful panel. Thank you, and we'll see you in April. Thanks.